Good morning. Today we get to learn about eigenvalues and eigenvectors. So I want to recap with a few ideas that we've been discussing all semester. Let's start with two vector spaces. So what we'll do here is fix a field F. And let's consider two vector spaces. Which we'll write in terms of circles and squares. So I want to remind you of a few different concepts here. First, remember that a map, which we'll call T, going from V to W, we say that this is well defined if T of x1 equals T of x2 whenever x1 equals x2. Remember, this here is just kind of a formality to make sure that we're working with something that has a nice definition. In the same sense, given a well-defined map, V is the domain and W is the codomain. So today we're not going to get into things like the range, the null space, so on and so forth. We also have the following proposition. Given a well-defined map, T, going from V to W, the following two statements are equivalent. So the first statement says, for all vectors x and y in the domain, and for all scalars, let's call them C, then we have two statements. So first, T preserves vector addition. So remember, what that means is, if I take a look at x plus y in V, then that's T of x plus T of y in W. Second property we want is that T preserves scalar multiplication. So what I mean here is, if I take a look at a scalar multiple in V, then that should correspond to the same scalar multiple in W. Right, so let's say that first T satisfies these two properties here. Well, that's equivalent to saying that for any collection of vectors. Let's perhaps call these v1 through vn, and scalars. Then we have the following. So if I were to take a look at a linear combination of elements in V, and then apply T to that, then I should get back a corresponding collection that looks like a linear combination of elements in W. So again, these two statements here are equivalent. And of course we say a well-defined map satisfying either of these is a linear transformation. So again, a well-defined map satisfying either statement 1 or statement 2 above is said to be a linear transformation. Okay, so we have the idea of a well-defined map, the idea of a domain, codomain, the idea of a linear transformation. And finally, I want to remind you of what do we mean by a matrix representation. So to every linear transformation, there's a few ways we can associate a matrix. So to this end, let's focus on the case where V is equal to W. And let's simply write V plus and dot. So I'm not going to focus on this funny thing of the circle plus and the square plus. Now I want to choose an ordered basis. And let's call this here beta. Perhaps corresponding to these vectors v1 through vn. I want to recall how to construct this funny symbol here, this T beta beta, that is the matrix representation of T with respect to beta. So what we do is this. Let's take a look at the image of every basis element and again try to write it in terms of the basis elements. So again, we take a look at the image of each basis element and try to write it in terms of these basis elements. So for example, if we take a look at what happens to V1, then I can write that as a linear combination of things. So this is perhaps A11 V1 plus A21 V2, maybe through AN1 Vn. That's what happens for the next one, V2. So this is A12 V1, A22 V2, AN2 Vn, so on and so forth, all the way down through Vn. So this is perhaps A1n V1, A2n V2, and then ANN Vn. So again, I'm trying to express the image of each basis element in terms of our basis. So once we have this, then we're going to make a definition here. Here, we'll list the following n by n matrix. If I take a look at the coefficients here, this will become the first column of our matrix representation. Right. And now, of course, I'll do this for all of the other columns. So here, let me just make a quick remark. If we denote the script L of VV as the collection of all linear transformations, say T going from V to V, then we actually have an isomorphism where I can relate here this set of linear transformations from V to V. This is isomorphic to the collection of n by n matrices, where what happens is the map sends a linear transformation to this matrix. The main thing to remember here is that given a linear transformation, once we fix an ordered basis, then we can always write down an n by n matrix. And there's a way we can go in the opposite direction. Given an n by n matrix, there's a way we can write down a linear transformation for that. But for today, we're just going to focus on the idea of fix a matrix. Now, there are a couple of types of matrices that we want to focus on. We say that T is diagonalizable if there is an ordered basis beta such that the matrix representation is a diagonal matrix. So very explicitly, what I'm saying here is that this matrix here perhaps has these numbers lambda 1, lambda 2, so on and so forth down to lambda n, where now all of the other entries here are 0. Right, so it just looks like we have these entries here along this diagonal. So this word here, of course, looks a little bit weird. All that this simply means is able to be diagonal. Right, so diagonalizable really is able to be diagonalized. So there is a way that I can find a basis to make this into a diagonal matrix. So that's what I mean here by this diagonalizable, that there exists a basis where we can do this. In a very similar way, we say that a square matrix A is diagonalizable if we can find a basis in this case. Our V is very specifically Fn, right, because in this case we're dealing with the matrix. Such that now the left multiplication by a matrix should be diagonal. So you can think of this as, we'll say that a matrix is diagonalizable if the left multiplication by a map is diagonalizable. As a quick remark, remember what's happening here. So essentially what this says is A is diagonalizable if and only if we can find an invertible matrix let's call it Q, such that the following matrix product, Q inverse AQ, is a diagonal matrix. Now, I'll leave the details of this in the lecture notes, but the rough idea is that once you do a change of basis, remember that the matrix here comes about from, say, the standard basis on Fn. Over here, we'll have a brand new basis, beta, and somehow the change of basis matrix from the standard basis to beta is where this matrix Q is coming from. Right. So what we're going to do today is really focus on these types of matrices, really on these types of transformations. So if you will, the goal that we have from here on out is to determine when a linear transformation or when a matrix is diagonalizable. And so I'll write that here. Now there's a couple more definitions I want to give here before we really start to get into what's going on. So remember that our ultimate goal is to determine when either a linear transformation or when a matrix is diagonalizable. So we're going to start this process by getting into what are called eigenvectors and eigenvalues. So let's make this definition here. Let's say that T is a linear transformation for a finite dimensional vector space V. Everything in this class is finite dimensional, so you don't really have to worry about this phrase very much. A vector, let's write this as lowercase v inside of our vector space, capital V, is called an eigenvector for our transformation T if there exists a scalar. Should really say two things. So one, V does not equal to the 0 element. And two, there exists a scalar, let's call this here lambda, such that T of V is lambda V. So remember again, this here, the symbol is called lambda. Now before I get too far, I want to say very quickly how that relates to this concept back over here. Well, let's say that our matrix is diagonalizable, so that means we can find the basis beta. So let's just quickly write our T is diagonalizable, and let's say that beta is the basis that works in this way here. Now, if you stare at this, and then remember how we define our matrix in terms of what happens with the vectors here, then this means that each T of Vi is lambda I times Vi. So in other words, if T is diagonalizable, then every element in this basis is an eigenvector. So somehow eigenvectors allow us to start to answer this question of when a matrix here, when a linear transformation is diagonalizable. All right, so again, we're going to play around with this in more detail, but right now just start to think that if it's diagonalizable, then the elements of the basis are eigenvectors. So the eigenvectors are the place to start if we want to answer this question, when is this diagonalizable? So of course we can do the same thing for matrices. So let's let A be an n by n matrix. So then we'll say that a vector V, in this case an Fn, is an eigenvector for A if two things hold. So number one, v is not the zero vector. And number two, a times v is lambda v for some scalar lambda. So I didn't say this up here really for the sake of space, but this lambda has a name as well. Lambda is called an eigenvalue. In fact, it's the eigenvalue associated to this vector v. All right, so we have this concept of an eigenvector and this concept of an eigenvalue. So if you will, there's a couple of motivating questions that we're going to focus on. So first motivating question. Given, let's say, perhaps a linear transformation T, or maybe even a matrix A, then the question is, can we find a basis beta such that maybe say this matrix representation of T, or perhaps let's say here the matrix representation for left multiplication by A says that one of these, let's say, is a diagonal matrix. All right, so either given a linear transformation or a matrix, can we find a basis such that this works? Again, if we have a basis, then they will automatically be eigenvectors, and so then we can find the corresponding eigenvalues. So more generally, how can such a basis be found? So you already know that maybe answering the question of kind of finding these eigenvectors, that might help to start here, but these are going to be our two questions. So of course we want to focus on these over and over. Now what I want to do, since I've just given a lot of definitions, is let's try to work out some geometric examples so we can really see what's geometrically the idea of an eigenvalue and an eigenvector. So let's do a first example. Let's consider the plane. Well, we are going to do real-life examples here. And let's fix an angle theta. Now, I want to consider the following linear transformation. So this T here will take a vector xy, and I'm going to write this in two ways. Either I can write this as x cosine theta plus y sine theta, and this here will be x sine theta minus y cosine theta. Or if you don't like this, we can write this here as a product of matrices. So here we have a cosine theta, Here's a positive sine theta, and now a negative cosine theta. Of course, remember that every linear transformation looks like it's the product of some matrix. So this here will, of course, be our matrix A. Right, this 2 by 2 matrix. So geometrically, this is a reflection about the line y equals mx, where m, it turns out, is tangent theta over 2. So here we can try to draw a quick picture to get a better idea. So let's draw our line. And if you will, this angle here is actually theta over 2. Right? So if I have a point here, maybe xy, then what's going to happen is this will simply be a reflection. So that'll reflect over to this point, t of xy. And now, I can see that this transformation here, of course, has order 2. So if I did this a second time, I get back to where I started from. But again, the angle here is just what we're calling theta over 2. As a quick remark, I should point out that if the angle theta is equal to 0, then of course m equals 0. And so what t of x does is exactly what you expect it to do. So it's just going to reflect over the line y equals 0. But of course, y equals 0 is exactly this vertical line here. And so this here just goes x and minus y. Right, so quite literally just reflects over here. Right? Let's see here. Let me be careful I'm saying this right. Sorry, I'm saying this wrong. When theta is equal to 0, I actually mean that it reflects over the line here. So more generally, if you want to pick any angle that you want, you can write down this more general transformation. But in the specific case for the angle 0, it will just be a reflection over the x-axis. So now let's just try to ask a couple of questions. So for example, what are the eigenvalues, eigenvectors? So we can do that using sort of what we had with the previous homework problem. Well, let's make a couple of observations. So first, we can observe that because m is the tangent of theta over 2, then cosine of the angle I can write as, well, 1 minus m squared over 1 plus m squared. And sine of the angle, I can write this as 2m over 1 plus m squared. And so if I really wanted to, I can then write my t in a form that should look familiar. So the matrix that we have here is 1 minus m squared Then here we have a 2m, 2m, and an m squared minus 1. All right, and again here, m says something about the angle. Next, what I want to do is, let's take a look at two bases. For v. So the first, of course, is the standard basis. So for the standard basis, we can write here 1, 0, and 0, 1. A second, I'll write here in terms of beta, and we'll write it this way. So here I'll put in 1m, and then here I'll put in a minus m and 1. Right. Now again, these here may look familiar. Let me try to place them here on the graph so we can see what do these represent. So maybe we can give some of these some names. Well, the first ones here, let's call these E1 and E2, of course, because they are the standard bases. So if we go back into drawing our line, y equals mx, then E1 is here, and E2 is here. Of course, here we have our 90 degrees. Now, what about these two here? So 1m minus m, 1. Well, 1m, we'll call this a vector v1. And the second one here, we'll call this v2. So v1 lies along the line, but v2 lies perpendicular to the line. Right, so we'll put that here. And v2 is perpendicular. Right. Now what we can try to do here is ask, what does t do to each of these four? So let's try to compute t on E1 in terms of the E1 basis. So this first one here, of course, is this. And let's say here, the second one, of course, is this. Right, so all that I'm saying here is that if I plug in x is 1, y is 0, then I should just get this first column here. If I plug in x is 0, y is 1, I should get the second column here. So if you put these two together, then our matrix A is just what we get by just putting in these as the columns. Right? But of course, this is exactly what I said here was our matrix A. Now, on the other hand, what happens if I ask, what are the images here for V1 and V2? So if I try to plug in things here for V1, then I get this. And if I plug in things here for V2, then I get this. But now if I stare at this, this here is just the same as V1, but here is actually negative V2. Right. Again, the way that we get this is by plugging in this here. So I plug in this for X, this for Y, into all of this. Here I plug in this for X, this for Y. Now there is a geometric way of seeing this. Right. So remember that here we have a map that just kind of flips everything over. Right. That's what T does here. But of course, if I'm along the line and try to flip it over, nothing happens. Right, that's the case here. Again, if I apply T to V1 and try to flip it over, nothing happens. On the other hand, if I'm sitting at V2 here and apply T, then you see that that's going to make it flip direction. So that's what it does to V2. But again, that's exactly what we see here. If you apply T to V2, it's going to flip everything over. So in other words, if I tried to compute the matrix representation now for beta, then I can just look at the numbers here, and I see that here I get back a 1 and a minus 1. Right, so kind of remember again, how do we define these matrix representations? So here's what we just realized. We see that number one, both A and T are diagonalizable. Of course, T is just the same thing as left multiplication by A. Number two, this basis beta we actually found just from looking at the geometry here. Right, so again, I just looked at one direction along the line. I know that nothing happens there. It's invariant. If I look at what happens perpendicular to the line, then she just flips everything over. Number three, both V1 and V2 are eigenvectors for T and A. And then finally, lambda 1, which is plus 1, is an eigenvalue associated to V1 and lambda 2, which is minus 1, is an eigenvalue associated to V2. Well, the way you see that is, of course, by these two here. Right? So T of V1 is some lambda times V1. T of V2 is some lambda times V2. But, of course, these are exactly the two lambdas here. So this example here is supposed to exemplify what we're going to try to do later, which is we'll work with the linear transformation, try to find our matrix A, and then hopefully write down the correct basis that will then tell us not only is the matrix diagonalizable, but also somehow we'll figure out what's happening with the eigenvectors and eigenvalues. So now that we have this example, let's try to see what happens in a very general sense. So from here, I want to try to write down some main properties and see if we can prove some of them. So in the book, these are actually 4 theorems together. Theorems 5.1 through 5.4. But we'll just think of them all as one. So of course, we're going to fix a linear transformation. Let's say here T, a basis beta, for V, and a matrix representation let's say A, which of course will just be the matrix representation, perhaps as I go from beta to beta. So there are 3 main results I want to write down. Right, so let's start with the first one. T is diagonalizable if and only if beta, this basis, consists of eigenvectors of T. Right, so that is that there's a basis where each of the vectors there is an eigenvector of T. Furthermore, this matrix A is a diagonal matrix and the diagonal entries let's write them as A, J, J. These here are the eigenvalues associated to each eigenvector Vj. So perhaps you want to think back to the previous example where here we have a diagonal matrix, so 1, 0, 0, minus 1, and each of the elements on the diagonal corresponds to an eigenvalue. Right, so this is part of a much more general idea. Okay. So here's the second of 3 results. Number 2, the following are equivalent. Right, so remember that means that if one is true, then they're all true, but one of them might not be true. So number 1, lambda is an eigenvalue. For t. Number 2, lambda is an eigenvalue for A. Remember, A is this matrix that we get from this basis beta. And number 3, the determinant of A minus lambda in is equal to 0. So now we're introducing determinants into the picture. And for the 4th one, there exists a vector different from the 0 vector such that this vector v is an element of the null space for this t minus lambda iv. So of course remember that iv here, this is the identity map. It just takes v to v. So this is kind of the avatar of like the identity matrix. And now the null space here is what I'm going to define as this E sub lambda. All right, so my E sub lambda is defined as this subspace here. So we're going to come back and play around with the subspace in a bit more detail. Finally, number 3, for any variable t, this n by n determinant which I'll call f of t. So it's the determinant here of a minus t times this n by n identity matrix. So this here has a constant term plus there'll be something times t plus something times t squared. And it goes all the way up to minus 1 to the n times tn. Right, so again, I have these powers of t. So this here is a polynomial. In fact, this is a polynomial of degree n. Right, because again, the highest power I have here is t to the n, which is independent of beta. Well, the beta here really comes about in defining this matrix A. So what I'm saying here is that once you fix any basis you want, what's left here really doesn't depend upon basis. If I choose a different basis, beta, then you might think that these numbers here are different, but actually they're all the same. So in particular, if I were to plug in t is lambda, like over here, an eigenvalue, then I see that f of lambda should be 0. Right, that was the statement over here. So I'm going to use this later to say whatever the roots of this polynomial are, those will correspond to the eigenvalues. So I'll use this to actually say a polynomial of degree n has at most n roots. So this actually means that this here will have at most n eigenvalues. So in particular, T has at most n distinct eigenvalues. Right, so these three here are really going to be the main properties for eigenvalues. So I made a statement here about this third part. Let me perhaps make a few remarks to piece together how is all of this going to help us. So let's say that we want to compute the eigenvalues of a linear transformation. Well, if we want to do this, I'll actually give you an algorithm. So step number one, choose a basis of V. Right, so any basis you want, it doesn't really matter. Number two, let's compute this matrix. This matrix A. Right, remember, this is just the matrix representation. Number three, compute this determinant. This f of t. Remember that this really is a function of the variable t. Right, so whatever this thing is, just compute this determinant. And then the last step just says find the roots lambda of f of lambda equals 0. So this here, again, is some polynomial. So you would tell your calculator, find the roots of that polynomial. Whatever those roots are, those would be the eigenvalues. Now I want to make a couple more remarks here before I move on. Well, there's a couple of things to notice. First of all, this polynomial f of t really does give you a lot of information. So f of t here, we give a name. This is called the characteristic polynomial of t. Now there's another little issue here. I've said that you can use this to compute the eigenvalues. Later, we'll see how to compute the eigenvectors. I know it seems kind of backwards, but actually it's a lot easier to compute the eigenvalues than it is to compute the eigenvectors. Okay. So I think what I'll do is I'll leave the proofs of all of these for the lecture notes, and then next time we'll come back and we'll try to focus on a few more examples of how to use all of this to actually compute the eigenvalues and eigenvectors. All right, so thanks for listening.